Good morning, Internet friends, and welcome to Dev Update number 1. I'm excited to show you some progress towards cryptographically verifiable elections on the blockchain. Since this is the first Dev Update, I want to get you oriented first by showing you the Git repos we'll be using and doing a little overview with diagrams of my planned development roadmap. Then we can get to the fun part, which is showing you my first version of the election script, which corresponds to milestone 1.1 in the Catalyst project. Let's get into it. I thought I'd start off by showing this one-liner that you can paste from the video description into your terminal if you want to follow along with the code I'm demoing today. Here's what it looks like when you run it. As prerequisites, you need to have Git installed, and you also need Docker as well as Nix. All it's doing is downloading everything, so hopefully by the time I get to the election script demo, you'll be all set to run it too. Alright, so you're clear on where all the code is coming from. I just want to show you a couple of Git repos. You've already seen this one before. This is the main repo for my project. But there's also this other second repo that I'm going to show you now, which is a fork of the official ElectionGuard Python reference implementation. There's also this newer C++ rewrite of ElectionGuard, which I'm not using anywhere. And that's because it's not feature complete yet. And it's also not nearly as well documented. So the first thing I did when I started this project is I took the reference implementation, forked it, and just made a couple little updates to clean it up and build a Docker image. Here's how to run that and verify that it's passing all of its internal tests. You probably don't need to do that right now, but it was important for me to do because when I'm developing my code, if there are mysterious errors, I need to know that it's because I'm doing something wrong and not just because I have the wrong version of a Python package or one of the cryptographic C libraries or something. Alright, so that's the first of 4 stages of development I'm planning. If I were to diagram it out, I'd start with a laptop, of course. And that laptop is running Linux and Docker. And then there's a single Docker container, and in the container is a Python script running its own internal tests, not interacting with anything else. So that's stage 1, which works already. Stage 2 will be the laptop again, but this time running what I'm calling the land stack: Linux, Arion, Nix, and Docker. Now there will be multiple Docker containers running, and each one will have a copy of ElectionGuard, but only be doing the parts of the election that would be done by one computer in the final version. For convenience, I'll control all of them with a top-level Python script. And to simulate a blockchain, I'll give them all access to a shared public records folder. For now, we'll just pretend that it enforces the rules that would be enforced by a blockchain, so files are time-stamped and immutable and digitally signed by whoever added them. The next step will be to swap out the shared folder for a little server. And what the server will do is maintain a set of public records that looks to the ElectionGuard container code pretty similar to a shared folder. But then on the back end, it's sending transactions to a Cardano testnet and uploading the files to IPFS. Then the final step is to separate the ElectionGuard containers so that the ones fulfilling a particular role in the election are actually on a separate computer. And the computers will only talk to each other through the actual Cardano and IPFS networks, and also by scanning some QR codes for things like smart contract addresses. I know that was a lot of drawing pretty fast, so just to recap, these are the 4 stages of my roadmap. The first is a single Docker container running Python code. Then I split the code into multiple Docker containers and let them communicate by a shared folder. Then I swap out the shared folder for a blockchain adapter server. Then finally, I separate the election roles into different computers and have them talk over the actual blockchain network. Stage 1 is done already. You saw that a few minutes ago. The main thing I want to show you today is that I also have the first part of Stage 2 done. Stage 2 corresponds to milestone 1 in the Catalyst project. And so today I want to show you the election script, and then the next couple dev updates will be on the verifier and the tests. Alright, so we're in the terminal, and we're in the milestone 1 election directory. And we're also inside a Nix developed shell. If you ran the one-liner from the beginning of the video, you should be here too and all set up to run the election script. Like this. It goes pretty fast though, so I'm going to add this extra argument to slow it down, so I can explain what it's doing at each step. First of all, this is the main config file election.json, and here the counts are what controls how many of each kind of container it spins up. So there's always one administrator, and then in this config I have 3 guardians and 4 encryption devices. The first step in the election is for the administrator to publish a manifest. There are lots of possible options in there, but I've pared it down to just the traditional pineapple referendum as a demo, which is, should pineapple be banned on pizza? There's just the one question and 3 possible answers. I've also scripted the number of votes for each answer, so we can come back and check at the end that the decrypted tally came out right. Alright, let's do the announcement. Now there are a couple more things to notice here. One is that the public records directory is bind mounted and then mentioned in each of the script calls. So it's here, and then here, and here. And then the other is the last part of the code I haven't talked about, these scripts. And these are bind mounted into each of the containers too. So you can see the main Python script calling them here and here. And there's one script per ElectionGuard role, so there's admin, device, and guardian. As an example, if we open up admin.py and scroll all the way to the bottom, then you can see it has a command line interface with one command per thing that the admin is supposed to be able to do in the election. So these first 2 commands, you can see it already calling here, are build manifest, which calls build manifest command, and announce key ceremony command. And then the rest of the arguments are just arguments to those functions. Cool. So if you watched the software stack video and then this one, you should have a pretty good idea how the code works structurally at this point. For the rest of the election, I'll just go through and give a quick overview of what all the files are for. There are 3 main phases to an election. There's the setup, there's the voting, and there's the counting votes. Let's go ahead and run the rest of the setup now. I'll do a separate video that goes into more detail about how guardians work and the key ceremony. But for now, all you need to know is that they each generate a public-private key pair, and then they publish the public key, and the 3 public keys get combined into a joint election key. And then that joint key is what the voting devices will encrypt votes to. Then to decrypt the votes, you need a quorum of guardians to cooperate, so in this case 2 of 3. Alright, let's do the voting. Couple things to notice here. One is just that I'm rotating the encryption device to simulate having 4 different polling places. But more importantly, each command here is doing 2 different steps at once that would be separated in real life. This is called the Benelo challenge, and I'll do a separate video on it too because it's probably my favorite part of ElectionGuard. But basically, the first step is that you submit your vote and the machine encrypts and uploads it. And then you have a choice about whether to cast or spoil it. Now if you cast it, that's your real vote and it'll be counted, but you won't get to see what it was. If you spoil it, then it won't be counted, and the machine will have to publish the decryption. So this way you can verify that it wasn't lying to you, but you also can't reveal your vote later. So for example, this ballot that starts with 488 was spoiled, so it's not going to be counted in the final tally, and we'll get to see the decryption of it at the end of the election. Whereas this one that starts with 4CC was cast, so it'll be part of the final tally, but we'll never get to see an individual decryption of it, which preserves ballot secrecy. So that's how voting works. The last step is to tally up the results. There are 2 things to notice here. One is that no one ever holds the private key corresponding to the joint public key. Instead, each guardian does a partial decryption using their share of the private key, and then the administrator combines those into one final decryption. The other thing is that there's only one final tally being decrypted, and it's the result of homomorphically adding together all the cast ballots, and I'll do a separate video on that too. So the things being decrypted are one final tally and all the spoiled ballots, but not the individual cast ballots. And that's it for today. The last step is just to print a summary and shut down all the Docker containers. If you want, you can also try changing some numbers in election.json and rerunning it to confirm that the final tally always matches. This has been Dev Update number 1. Join me next time and I'll go over the verifier, which is code that you can run with a set of election artifacts generated by someone else to check that there aren't any irregularities.